Hey everyone, welcome to this explainer. Okay, so today we're literally going to completely flip your understanding of gravity, mass, and how things actually fall in our universe. Because, well, if you think you really understand what makes things heavy or, why an astronaut floats around in space, get ready because we are about to look at the invisible forces shaping our reality in a totally new way. Here is our quick roadmap for today. We're going to start with a really simple earthly experiment, break down the math behind it, take a quick trip to other planets, and finally, figure out exactly how satellites manage to stay up in orbit.
All right, let's jump right into section 1, the gravity illusion. Time to test that intuition of yours.
So I really want you to trust your gut on this one. Picture yourself standing way up on the roof of a tall skyscraper. In your left hand, you're just holding a tiny little grape. But suspended by a massive crane right next to you is a huge, heavy grand piano. Now, if they're dropped from the exact same height at the exact same fraction of a second, which one hits the ground first? Our intuition absolutely screams that the piano, being thousands of times heavier, just has to plummet to the earth faster, right?
Well, moving on to section 2, the fall of man, let's actually test reality and see if your gut feeling holds up.
To answer that piano and grape question, look, we obviously don't need to rent a crane. We can just do a really brilliant, simple physical experiment called the fall of man activity right here in a classroom. The setup is incredibly easy. First, just grab two objects with totally different masses. Like a heavy metal weight and a regular wooden pencil. Second, hold them out in front of you at the exact same height. Third, count backward from 3 and drop them absolutely simultaneously. What you're going to see is going to totally shock anyone who bet on the piano. They hit the floor at the exact same time.
Now, a quick heads up. If you try this yourself and one object does seem to hit a tiny fraction of a second later, actually scratch that. It's almost always just human error or air resistance. Like if you drop a flat piece of paper, it kind of floats down slowly, right? That's just the air pushing up against its wide surface. But tightly wad that exact same piece of paper into a tiny dense ball and drop it right next to the pencil, bam, simultaneous strike. So yeah, don't go blaming gravity for a bad throw.
So here is the absolute aha moment. We really have to separate two massive ideas in our heads. Mass is intrinsic to matter. It's literally just the amount of stuff packed into an object. A grand piano has a whole lot of stuff, a grape has very little. Weight, on the other hand, is the actual force of gravity acting upon that stuff. The reason the piano and the grape fall at the exact same rate is because a falling object's acceleration doesn't care about its own mass at all. To really get why that is, we've got to look at the numbers.
Which brings us nicely to section 3, Newton's universal law. Let's look at the math behind the magic. Way back in the 17th century, Sir Isaac Newton had this huge light bulb moment. He realized the force keeping the moon up in the sky is the exact same force pulling an apple down from a tree. His equation, F equals gmm over r squared, might look a bit intimidating, but it tells a really beautiful story. F is the force of gravity. G is the universal gravitational constant, which is basically just a tiny baseline number for gravity everywhere in the universe. Big M is the mass of the giant object, like planet Earth. Little m is the mass of the smaller object, like you or an apple. And r squared, that's just the distance between the centers of those two objects.
Okay, so check this out. If we take that equation and plug in Earth's specific mass, which is a mind-boggling 5.96 times 10 to the 24th kilograms, and Earth's radius, we get this magic number, 9.8 meters per second squared. We call this little g. It's the acceleration due to gravity on the surface of our planet. But wait, did you notice what was completely left out of that final calculation? The little m. Your mass, the grape's mass, the piano's mass, it all completely cancels out of the acceleration equation. That means absolutely any falling object near Earth accelerates at exactly 9.8 meters per second squared, 100% regardless of its own mass. Crazy, right?
All right, section 4, weight on other planets. Time to scale this up.
So if your mass doesn't dictate how fast you fall, what happens if we totally swap out the planet beneath you? Because a planet's gravitational pull depends entirely on its own total mass and radius. Every single world has its own unique acceleration rate. Just look at Jupiter. It's massively heavier than Earth, so it pulls you down with an intense acceleration of 23.1 meters per second squared. Meanwhile, our little moon has a tiny mass and radius, giving it a super gentle pull of just 1.7 meters per second squared. Remember our definition from earlier? Your mass, the actual stuff making up your body, stays exactly the same on all these worlds. But your weight? That shifts dramatically.
To really put this into perspective, if you stepped on a scale here on Earth and it read exactly 100 pounds, taking that exact same scale to Jupiter would be a literally crushing experience. You'd weigh 2.4 times more, 240 pounds. But if you took a quick trip to the Moon, you'd feel incredibly feather light, weighing in at just 17% of your Earth weight. A mere 17 pounds. Same exact mass, totally different weight, all because of the planet's unique gravity.
Okay, finally, Section 5. Orbit is just free fall. Let's push this concept to the extreme limit. So we've been talking about things dropping straight down, but what happens if you throw something sideways, like insanely fast? Let's look at the NASA Swift satellite, operating about 600 kilometers up. It's not just magically hovering up there, it's actually utilizing centripetal force. Swift is moving purely horizontally at a blistering speed of roughly 7,550 meters per second. Because it's cruising horizontally so incredibly fast, the centripetal force it needs to stay in a circle is perfectly supplied by the downward pull of gravity.
Honestly, this is the most mind-bending reality of space travel. Being in orbit simply means you're moving horizontally at just the perfect rate so that as you fall vertically, the Earth physically curves away beneath you. Satellites and spacecraft absolutely do not escape Earth's gravity. No way. They are falling constantly, forever, but they're moving sideways so incredibly fast that the round shape of the planet just drops away at the exact same rate they're falling. It creates an endless circular path.
And you know, this completely shatters one of the biggest misconceptions we all have about astronauts. When you see them just casually floating around the International Space Station, you probably assume it's because there's zero gravity in space, right? But out at their altitude, they're actually experiencing about 85% of Earth's normal gravity. They aren't actually weightless. They only feel weightless because they, along with their entire spaceship, are in a continuous, sustained state of freefall. It's exactly like that crazy stomach drop feeling you get when a roller coaster plunges down a steep hill, except they are experiencing it permanently.
So I'm going to leave you with this final thought to chew on. If gravity reaches all the way up into space to hold satellites in orbit, and astronauts 600 kilometers away still feel 85% of Earth's pull, how far out into the dark, massive universe would you actually have to travel to truly weigh absolutely nothing? Well, according to Newton's law, the answer is that gravity extends forever. It gets weaker, sure, but it never ever truly reaches zero. Keep questioning the universe around you, students, because the underlying mechanics of our reality are vastly more fascinating than they first appear. Thanks for hanging out with me on this explainer.